You're welcome to day 33 of 50 days of tutelage. In today's class, I'll be talking about chemical kinetics. And basically, what this class is going to be all about is about talking about the rate of chemical reaction. The rate of chemical reactions. And we're going to be looking at how reactants, so we have reactants being used up, and as they are being used up, products are being formed. So we want to look at the rate at which these guys are disappearing and these guys are being formed. And note that the quantity of the reactant that we are going to be considering, we can be considering the mass of the reactant, we can consider the concentration of the reactant, we can consider volume of the reactant, and other things like that. So it could be that we're considering how much mass of reactant is being used up to become some mass of the product that is formed, or the concentration or the volume as well. But for this particular video, I'm going to be focusing on concentration. So we can see rate of a chemical reaction is simply the change in concentration of reactant. So I'm going to be using the square bracket for to represent concentration with respect to time. So it is change in concentration per unit time. That's basically what rate of reaction is all about. However, you can also define this thing based on the product as well, because as the reactant, as it is disappearing, the product is being formed as well. And these two depend on each other. It is the disappearance of one that leads to the appearance of the other. So, but I'm going to be focusing on using the reactant here, but the product can also be used as well. Now, let's proceed. But for reaction to be feasible, that is, for reaction to take place, there are like few things that must actually happen. And these few things that must happen is explained by the collision theory. Is explained by the collision theory. Is explained by the collision theory. And what is the collision theory? What the collision theory basically explains is that for particles, for reaction to occur, there must be collision of particles of the reactant. That is, the particles of the reactant must collide together if there's going to be a feasible reaction, if reaction is going to occur in the first place. But this collision of the particle is necessary for reaction to occur. However, it is not a sufficient condition. For the condition to be sufficient, there are other conditions that must also be satisfied. For instance, the particles must be properly aligned. They must be properly aligned together. And not only that, they need a certain amount of energy before they can happen. They need a certain amount of energy before they can happen. So let's say, for instance, now they need to absorb this amount of energy. And this amount of energy that they need to absorb before the reaction can take place is called the activation energy. So denoted as EA, it is called the activation energy. So therefore, for reaction to take place, number one, the particles of the reactant must collide together. But not only will they have to collide together, they must be properly aligned and they must possess a minimum amount of energy known as the activation energy. If they possess anything less than this energy, the reaction will not take place. So therefore, they need something from that minimum or more than it for the reaction to take place. Now, let's now look at what determines what type of reaction is really taking place. So I'm going to draw a kind of energy profile. So let's look at this. So here we have energy, and then let's say here we have so this is the reactant side. So I'm just going to label that with R. Now, as this reactant, as they are colliding and they do all of those things, then there's a kind of going up, a rising up to a certain amount of energy. Let me not make it go past the graph. Yeah, to a certain amount of energy, and they get to this point. Now, when they get to this point, if this energy is their activation energy, it means that at this point now, reaction can begin to take place. So this place, let's call this place EA. And what is going to happen is that before they get to this particular energy, reactant absorb the energy. So this activation energy was absorbed. Now, so what now happens is that some amount of energy will now be released in the process to form product. Some amount of energy will be released to form the product. Sometimes this energy that is released can actually be more. And sometimes the energy that is released can be less. For instance, you can see how much this guy has to go up from this level, this minimum level, to this maximum level. But if, let's say, the energy should drop to something around this point, so if the energy should drop to something around this point now, so what you will notice in this place is that how far this thing goes up. So if you measure this height now based on the energy now, and if you measure this level now, you notice that this is actually smaller than the one on the left. And because of that, that implies that smaller energy has been released to the atmosphere. And this place, the product is actually formed. So the product is formed in this place. And what happened here is that you see that the energy level for the product, so let's call this HP, and this is the energy level for the reactant. In that place, the energy level for the product is greater than the energy level for the reactant. And so therefore, if you find their change in energy, you have HP minus HR, and this result will be greater than zero. That is, it is going to be a positive result. So it is characterized by, okay, absorbing of energy, you get to the activation energy, then there's a release of energy into the environment, into the surrounding, and the product is formed. But the amount of energy released is not that much. So therefore, you are at a higher energy level for the product. And this reaction is known as endothermic reaction. So this reaction is known as endothermic reaction. So as you can see now, delta H is positive. And so this right here, from this point to this point, is where you have your delta H. Delta H is positive. This is for endothermic reaction. Also, this particular level, this peak here, now this peak is actually known as the activation complex. This place is known as the activation complex. It's a point whereby this whole reaction, the whole system is unstable at this point. So therefore, energy just has to be released. The change in energy from down to this place, from the reactant side to this activated complex, is what is called the activation energy. So, but this point here, this maximum point here, is called the activation complex. Now, the same scenario, so let's say we have the same setup. So you also have the energy. I'm not going to be doing too much of labeling here because I've already explained. So you have the reactant proceeding, you have the reactant like this, then you have this go up to that point. So the earlier case, so this is the reactant, earlier case had said that the fall is not as much. So the energy released is not as much. But if you have a kind of higher surge of energy released and you have something of this nature, yeah, such that it is at this point that the product are now being formed. So in this place, you have the product. So what you notice there is that this level now is your HR and this level is your HP. And so if you notice that now, you notice that HP is less than HR. So therefore, if you find delta H, which is HP minus HR, that is going to be a negative result, which is going to be less than zero. That is going to be less than zero. So that is negative. And this describes an exothermic reaction. So every other thing that I've labeled still holds. This is an exothermic reaction. And so this is basically the foundation of feasibility of reaction. I'm not going to be going into too much details about that, but at least this will help you understand any other thing that you have to know about that. So that is explaining the collision theory. We know that it is necessary for collision to happen before reaction takes place. But also, while it is necessary for collision to happen before a chemical reaction takes place, there is also, it's not sufficient. You need a minimum amount of energy, and you also need the whole condition to be properly aligned before the reaction is feasible. So now let's talk about the factors that actually affect the rate of chemical reaction. So the number one factor that affects the rate of chemical reaction is concentration of reactants. Concentration of reactants. So I'm going to explain that now. Number one, concentration of reactants. Now, what do we mean by concentration? Concentration is actually always a measure of one thing over another. Of course, the usual one that we are actually used to in chemistry is always solute versus solvent. But I want to define concentration in a general sense now. For instance, let's say there is a room, and let's say this is a room. And you want to fill people inside this room now. So let's say you have person A, person B, person C, and person D. These are people anyways, not nine. Now, the same room again, so I'm just going to copy the room. The same room again, you want to fill the room, and then you begin to have this person A, person B, person C, person D, person E, person F, person D, and on like that. So what you notice is that it is the same room, but we have different number of people in these rooms. And this room seems to be more populated. This room now, the same room, but the one down here seems to be more populated than the one here. So what has happened here is that you are considering concentration of, so the A will be the people and B will be the room. So when we say concentration now, this is actually more concentrated than this other guy. So therefore, you have a higher concentration for this. And the same thing. So how actually does concentration affect the rate of chemical reaction? How does it affect the rate of chemical reaction? So from what we have said earlier, there must be collision. And this collision, there must be a kind of minimum amount of energy and blah blah blah. But for collision, since collision is necessary, between these two between these two scenarios now, scenario one and scenario two, which one do you think will have more collision taking place between the particles that are inside? Of course, it will be scenario two. So therefore, when concentration increases, rate of chemical reaction also increases as well. Because now you can have more collision take place. You can have more collision take place because now there are many substances in the same solution. Therefore, there will be increase in chance of collision, and that is for concentration. The next one is temperature. The next one is temperature. So, what is the effect of temperature in this in the in terms of rate of chemical reaction? Of course, the first thing you know is that temperature always increases kinetic energy. If you've been following the class, I define temperature self as the measure of average kinetic energy. So if you increase temperature, automatically kinetic energy will also go up as well. And that's even, it gives room for you to be able to reach the activation complex very, very fast because now you have more energy in the system, and so reaching the activation complex will be a lot faster because now something is actually increasing the energy. But not only that, when you increase the temperature, these guys gain kinetic energy, and therefore they are likely to move more randomly. And this, the more random that they are moving, then the more the collision is going to happen. So temperature is kind of doing two things here. Number one, it is increasing the kinetic energy in the system. This kinetic energy in the system in turn is actually causing more collision to happen. So therefore, there will be increase in the rate of what? In the rate of chemical reaction based on increase in temperature. Another one is surface area. Surface area. Now, this surface area, for you to understand the concept of surface area, if two reactants, reactant 1 and reactant 2, if they are going to react with each other. So let's say this is a reactant. So let this be a reactant and let this be another reactant. So I'm going to show you something here. I'm going to be moving this thing around. For them to actually react, there must be collision between them. So I want to show you something now. Look at this first instance. So let me do this. This is the first instance. So let me just put this here. Let me put this. I just want to have three of them like that. So I want to show you something now. So in this first case, look at the way they are arranged. In the second case, look at the way they are arranged. And in the third case, I want you to look at the way they are arranged. So I want to ask you a question now. Between A, B, and C, which one do you think more collision will happen between the reactants? By the way, let me label them. This is reactant 1, reactant 2, reactant 1, reactant 2, reactant 1, reactant 2. So what you notice is that this one gives room for few collisions to happen because the particles that are allowed to interact are not really that much. Of course, this one tried to close the gap a little bit, but it's still not as much as what this second guy is doing because this one allows more of the old guy to actually interact. Just imagine they now overlap each other. That is, this is actually right on top of this. That would also mean increase in surface area as well. So when you increase surface area, you're actually increasing the rate of chemical reaction. Why? Because you are exposing more of the particles that are reacting together. You are exposing them to be able to react much better. And so that is what how surface area affects the rate of chemical reaction. The next one is the introduction of catalysts. Introduction of catalysts. What are catalysts? Catalysts basically they affect the rate of chemical reaction, but in the process they are not being used up in the chemical reaction themselves. So catalysts are more like a substance that they could be reactant on their own, but in the process of using them as a catalyst, they are not reacting. They are just there to change the way the reaction is going. By the way, sometimes they can increase the rate and they can decrease the rate. But here we are mostly interested in the ones that will favor it. That is why we can have a positive catalyst and we can have a negative catalyst. Positive catalyst increases the rate of chemical reaction, but some negative catalysts, that is, some catalysts that are called negative catalysts, they decrease the rate of chemical reaction, meaning they are trying to slow the reaction down based on what you want. But I'm mostly interested in the ones that are positive now. Now, they're not being used up in the chemical reaction. In fact, sometimes if you see them probably go through a reaction, what you realize is that when the entire product is formed, they are going to see them again. For instance, let's say you have A plus B, and this gives us C plus D. Then automatically you now have C plus D. It now gives us, let's say, E plus B again. So this, I've broken down reaction in phases now. So this is phase one. It proceeds to this point, then it proceeds to phase two. So A plus B produce C and D. Then C and D continue the reaction and they produce E and B. So you notice that B that you started with is now here again. It means that this B is actually a catalyst and the net reaction is actually going to be A producing E, because when you do everything together, A is actually going to be the one producing E eventually. So B there is a catalyst because it did not take place in the chemical reaction. And so let's now see what catalysts, let's see what they do. What they do is that they don't actually necessarily change the reaction. They don't change the reaction. They only change the rate. So the reaction will still go as it is. And what do? They actually provide another path for the reaction to go on. So for instance, if you have something of this nature now, let's say this is the reaction path. This one is for, yeah, this one is actually for exothermic reaction. This one is for exothermic reaction. I'm trying to make it a little bit small. Anyways, this one is for exothermic reaction. Now, this is the normal reaction pathway. But if you introduce a catalyst into this system now, the catalyst will still go through this route, but now it goes something of this nature, and now form the product. So the reactant and the product. So this is the introduction of the catalyst. So let's call this one the activation complex 1. This one will be the activation complex 2. This one is actually the new one provided by the catalyst. So what catalysts do is that they provide a new reaction pathway. So instead of you having to absorb this much energy before you can become spontaneous, catalysts, they make you attain less. So what happens is that activation complex is lowered when you're using a positive catalyst. Activation complex is lowered, or you can also say that activation energy is also reduced as well. That is what majorly the function of catalyst. They do that, and so therefore reaction takes place fast. So imagine you don't have to attain much energy before before reaction becomes feasible. That implies that reaction is going to be happening very faster than than when you have to attain a certain amount of energy. And that is what exactly the introduction of catalyst, that is what it means in this situation. So I'm not going to be doing too much of exegesis. I believe you understand all of these things that I've explained so far. By the way, if you are enjoying the class so far, you should like and subscribe to the channel. Thank you. Let's proceed to the last thing I want to talk about today is the rate law. The rate law and order of reaction. Why did I write it like that? Rate law and order of reaction. So what is rate law and what is order of reaction? Now, rate law is just simply a way of representing how So a mathematical way of representing how a reaction goes. So it's like an equation which we experimentally determine. And then once you see that equation, you can easily tell, oh, this is what is happening to this particular whatever and all of those things. So generally, you have rate is given as K, A raised to power M, then multiplied by B raised to power N. Note that this represents for an equation of reaction such that you have something of this nature. You have something of this nature. You have A plus BB, and then this guy is forming the product. Is forming the product. So this M and N, they will be determined experimentally. They are called the order. They are the order of reaction. They are called the order of reaction. Of course, R is the rate, and K is called the rate constant. K is the rate constant. Whenever I use square bracket like this, I mean molar concentration. Molar concentration. So let me quickly talk about this order. So for you to understand the order of a chemical reaction, know that you can decide to describe the order of this reaction using A only. So order of this reaction with respect to M is order M. Order of this reaction with respect to B, sorry, with respect to A is order M. With respect to B is what? Is N. But if you want to talk about the overall order of the reaction, then that will be M plus N. And this actually tends to affect the whole rate. It affects it differently. For example, if you have a reaction with A and B, and let's say you have A to B order 2, and then B is of order 1. So I will just not put anything there. So let's see what happens if you double this concentration of A now. What will actually happen to this eventually? What will happen to the entire rate, entire rate of reaction? So you double it. So what happens is that R equals, I think I should triple it instead. So that is multiply it by 3. So let's see what is going to happen. So you have this triple, that will be K. This time around now, you have 3 times the concentration of A. Everything is raised to power of 2. Then B, nothing has happened to it. So this rate will now become, let's call this one R naught. Now this rate will now become K multiplied by, now when you do this together now, this will be 3 raised to power 2, that's 9. So that's 9 multiplied by the square of the concentration of A multiplied by B. And so what do you notice here is that this is actually the same thing as 9 times 9K multiplied by concentration of A squared multiplied by concentration of B. And this R is then equal to, now this entire thing, K multiplied by concentration of A squared times concentration of B, is the same thing as that previous rate, and that will be 9 multiplied by R naught. So when you have something of order 2, the moment you you increase it by a particular factor, then the new rate is actually going to be a kind of power of that initial order, a power multiple of that initial order. I'm trying to put that in a better way. So what I mean is that, so for instance, let's say you have to like quadruple it now. That is, you do it 4 times. That means that the new rate is going to be a power which is 4 raised to power 2. That will be 16 multiplied by R naught. That's basically what I'm talking about. So you can see how this rate is affecting the order of reaction, and then how it is increasing the rate of reaction as well. So it can be of order. By the way, the overall order of this reaction is going to be, this is 2, this is 1. So overall order of reaction is going to be 3 for this. But with respect to A is order 2, with respect to B is order 1. So for order 1, so that's why we have what we call the zero order reaction. We have the first order reaction, we have the second order reaction, we have the third order reaction, and it goes on like that. For this zero order reaction, R will just be K, because every other concentration there will be raised to power of 0. So R is just going to be equal to K. For first order reaction, R will be Ka, then B raised to power 0. Or you have Ka raised to power 0, then you have B. So one of them will be the one that is carrying the other. Then for this one, R is Ka. You can have Ka then B. So you can see both of them are 1, 1. So that's 1 plus 1, that's 2. Or you can have K A raised to power 2, then you have B raised to power 0. Meaning that A is the only one taking care of the other. And you can also have Ka raised to power 0, then B raised to power 2. So all of these are also still second order reaction. And you can tell what the third order would be like that. So third order, you can have A as 2, B as 1, A as 1, B as 2. You can have A as 3, B as 0, 0, 3, and it can go on and on like that. That is the way they can be like that. So we have first order reaction, second order reaction, third order reaction. And so you can see the way they are being affected. So if you're considering A only, and if you're trying to join B as well, you can always do them out like this. And that's basically the summary of what rate of reaction is. Because of time, I would have taken an example, so I will just limit it to this at this point now. So that's it for today. I'll see you in the next one.